All right, so welcome along, ladies and gentlemen, to your weekly SETI Talks series. We're here at Microsoft Research, and we're going to be hearing a talk today from Xander Tielens. Xander is located at the University of Leiden at the moment. That's where he did his doctorate. Soon after he did his doctorate at Leiden, he came across to do a National Research Council postdoc at NASA Ames. And he has had a very close affiliation with NASA Ames, spending a total of more than 18 years at Ames doing his research. He also went to UC Berkeley in that time, soon after his postdoc, and then in 1997 returned to the University of Groningen in the Netherlands. And since 2009, he's been a professor at University of Leiden. So throughout his career, he's been most well known for his groundbreaking work in polycyclic aromatic hydrocarbons in the interstellar medium of space and their observations and working out how they tick. For example, he's looked at the chemistry of molecules, particularly in photodissociation areas where in the far infrared there was a lot of UV photons that dominate the chemical reactions that are happening in those areas. He's also interested, of course, in interstellar dust and grain surface chemistry. In 2012, he was awarded the Spinoza Prize, which is the highest prize in science in the Netherlands. And he also became a member of the Royal Netherlands Academy of Arts and Sciences in that same year. Today he's going to talk to us about the links between astrochemistry and astrobiology. So please join me in welcoming Xander.
Thank you for inviting me here. When I said yes to coming to the Bay Area around this time of year, I fully expected the Giants to be in the playoffs, but I hadn't realized that this was an odd year. But nevertheless, it's very nice to be here, to be back here again. We'll be talking about astrochemistry and the links between astrochemistry and astrobiology. And I want to start off with a little introduction to really bring across to you what special times we live. This is a very special moment in our history because we are realizing things that we didn't know before. And nowhere does it sum this up better than in this slide that comes from the Kepler mission, which shows the Kepler planetary systems, where there's more than one planet known. The relative size of the planets is okay. The relative size of the orbits is okay, but of course the size of the planets compared to the star is not. But the main point I want to bring across is that planets are everywhere. Every star in our galaxy has a planetary system. And basically, there's 100 billion stars in our galaxy. And there are 100 billion galaxies in the universe as known to us. And that's 100 billion times 100 billion, that's 10,000 quintillion. Probably you did that quickly in your head. I had to look it up. I had to look up that word. But it's a lot of planetary systems. Now, many of these planets are, as depicted here, they're close to the host star, they're very inhospitable, hot, and molten rocks and whatever. And so those are not the planets that we're really interested in. Those are not the planets that we're looking for. The planets that we're looking for are, the Goldilocks planets. You probably remember the story. I told it many times to my children. You know, Goldilocks went hiking in the, walking in the forest, came across this little cottage. She went inside, she found the porridge, and this porridge was too hot, this porridge was too cold, but this one was just right. This chair was too hard, this one was too soft, but this one was just right. We're looking for the planets that are just right for life. And we have found some. These are some artist impressions of what these planets look like. Kepler 20e, 20f. They are rocky-like, and they're close in habitable zone where water would be liquid. And so that's one criteria that we use to discern whether planets are of great interest to us or not. And one of the main results of the Kepler mission was this eta-Earth factor. 1/5. Eta Earth is the number of stars like the Sun who have a planet like the Earth in an orbit where water would be liquid. 1/5 of those. That's a gazillion. You know, that's an enormous number of planets where life could be present. And this is, I cannot impress this enough. This is really so different from what it used to be. I remember in the late 70s, there was this old astronomer, you know, he's probably my age now, and he was going around, he had been studying photographic plates taken at his observatory for 50 years. And he had been looking at the motions of Barnard's star. Barnard's star is a close-by star which has a proper motion, so it moves relative to the stars in the background. And he had been looking at this, and he had discovered that the path of that planet wobbled a little bit. And so he took from that there was a companion, and that companion had to be a planet. So he was going around saying that planets, yes, planets were out there. Planets were... how should I say, the reaction were mixed to this. He believed he was right. Nobody else believed that was true. And nobody was in fact correct, because this is the one star that we have not found a planet around. In fact, there is no planet in the position where he thought planets were there. But basically, the wobble was because they cleaned the telescopes regularly and the objectives, and then they put it together slightly differently. The optics were slightly differently, and it's just a very difficult and a very hard measurement to do. Certainly if you had to do it with photographic plates, certainly if you have to do it over a time span of 50 years. Nowadays, with missions like Kepler, we can go out and we find planets everywhere. In fact, we're already taking the next step. That's trying to decipher what the composition is of the atmospheres of these planets. Because in the end, we want to know what is in these atmospheres, and could there be life on these planetary systems. So this is one of the very first measurements of this. Is a near-infrared spectrum running from about 1 to 2.5 microns, and the symbols are the actual measurements. The orange and the blue are the models, and they are just here to illustrate that you can try to decipher from this the composition of the atmosphere, and therefore something about the planets themselves. So this is one thing that has changed over the last 20 years. We have learned that planets are everywhere. Earth-like planets are everywhere. Other thing that we have learned is in the realm of biology, and this is a very nice example of that. This is the Grand Prismatic Spring in Yellowstone, and you see the scalding hot water. You see the steam coming off. The water is of the order of 70 degrees or so, 70 degrees Celsius, excuse me. And so it's close to the boiling point. Every year there's an unfortunate person who falls into this and has to be transported to the hospital. So it's very difficult to be alive, but you can see those nice colors here. Those colors come from cyanobacteria. So there are nice bacteria living in these very hot environments that we didn't think that life could exist. And so that's very different. This is for a very hot place. Here we are looking at a Antarctic lake under the ice. It's very, very cold. We can see here these nice stromalite bacteria colonies. So these haven't probably changed in billions of years. And it's very cold location, and so even in a very cold environment, you can have these extremophiles. So life can be in many different places. This is another example. This is the Atacama Desert. It's sort of the driest spot on Earth. It's at the Chilean Andes Plateau. It's really very dry, but if you go into the earth, you dig down to about, I think this is about 10 meters. You find these salt crystals, and on top of these salt crystals, you find these bacteria. They are growing on these salt crystals. The salt basically collects the vapor from the air and concentrates it there. That's why the bacteria can live there. We can see that life can be adapt to many different environments, can live in many different places under very extreme conditions, from very hot to very cold, from very dry to very wet. And so that's something that we have learned over the last 20 years as well, that life is very adaptable. This is then the last point that I want to make. This is a lifeline of the Earth, so we are here. Here's the beginning of the Earth, 4.56 billion years ago. And this very first period is called the Hadean period, because at that point we started to put the Earth together, brought all these rocks together. It was very hot, molten lava surface, not very nice place to have life. This is where the moon was formed some 30 million years after the formation of the Earth. Then we have the oldest rocks that we can find are these zircons from the Jack Hills in Australia. They date back to maybe 100 million years after that. So at that point, the surface started to solidify. At that point is when you can start to think about, oh, can we start to make life? Then here's the late heavy bombardment, some 800 million years after the start of the formation of the Earth. So that's a point where rocks were brought in from the outside. Large impacts occurred. If any life had been formed before that, it would surely have been erased at this point. And then the first fossils are somewhere here, and that's only a few 100 million years later. So as soon as life could be established, it did establish. And I think that's another message that we should take along as well, that it is apparently very easy for life to form once the conditions are right. So the key questions that we have, basically it's the key question that we face as humanity. It's the question that defines humanity. Are we alone in the universe? Are we special? And these are this question translated into an astronomical context. So if you want to build new worlds, what are the key processes that take place? How do they depend on their environment? What is the inventory of planets that you can find in the universe, and particularly in the habitable zone? That's the kind of realm where Kepler lives. And once you have formed your planetary habitats, what is the origin of the organics and the volatiles that you bring to this environment? And what are the processes that play a role in their delivery? Then once you have that, you can ask the question, well, what are the conditions on this early Earth and newly formed planets? And what are the key processes that play a role in setting the stage for life? And so the one that I will be focusing on, some reason, there it is that second one. So what is the origin of the volatiles and the organics that are delivered to the Earth or to newly formed planets, and what are the processes that play a role in their formation? And so let me take you to a few steps that sort of summarize the different processes that play a role in putting the Earth together, and that tell you where do those building blocks come from. And we start off with this one here. This is, we are going to build planetesimals one grain at a time. And this is the distance from the sun. This is the mass of your planetesimals. And you can see this is time scale. You start to form, in this particular calculation, you start to form planetesimals very rapidly in a few thousand years. At that point, you isolate them. At that point, you can start to build planets from those planetesimals. But you can see there's a second stage, that material that comes from further out, at some point starts to drift in, and you get this hail of pebbles that come in that can get captured as well. And the thing to remember in this is that this is close to the sun, so here it is sort of warm. This is far from the sun. This is where it is cold. And so you can get very hot materials, rock-like materials getting together in the beginning, forming your planetesimals, but you can still add fairly cold material formed at much further out, much more benign conditions, and you can bring them in at a later time, well, a later time being about 100,000 years. So that's how you form your planetesimals. Once you have your planetesimals, you can start thinking about forming planets. Here we have the inner solar system. The sun is here. Here's where we want to form the Earth. Jupiter is somewhere on the outskirts here, and it's setting this whole thing astir. What's plotted here is the distance from the sun. This is the eccentricity. And if you have a very eccentric orbit, that means that you make passages to the inner region where it is denser and where you can be collected by the planets that are being formed. And then this color scale here is indicating, well, these are more rock-like elements, but here you're cold enough that you have water and organics present. And you can see that in the beginning you only form things from the rocks, but later on you start to add the water from the region which is now where the asteroids are. So you can see that you can transport organics and volatiles inwards to a location where you wouldn't expect it to be present in the beginning. So this is, now we have formed our planets about 200 million years. That's when we say, oh, it's about done. You've cleared out the environment, and we have 3 planets. That's sort of good. We lost Mercury, I guess. You know, some people would say it's not a big loss. Maybe the Mercurians wouldn't agree. So that's the second stage. The third stage, where you can start to collect material from throughout the solar system, is after 800 million years. That's when you have the late heavy bombardment. And here we have a little video. This is the sun. This is the orbit of Jupiter, Saturn, Neptune, and Uranus, and around it is a cloud of cometesimals. And these cometesimals interact with mainly Jupiter, and some get scattered outwards. And when they get scattered outwards, it means that Jupiter moves a little bit inwards. Saturn moves at the same time a little bit outwards, and not much happens until you hit 800 million years. And that's the moment that you really have to pay attention, because there it is. All of a sudden, Jupiter and Saturn get into resonance. And when Jupiter and Saturn get into resonance, that means that they're pushing at the same time, and that means that they scatter all those cometesimals. Most of them get scattered outwards, leave the solar system, but some get scattered inwards, and when they get scattered inwards, they bombard the inner terrestrial planets. That's where the craters on the moon come from. On the Earth, they impacted, of course, as well, but on the Earth, that record is largely disappeared. And so if you had paid really very close attention, then you would have seen that at this point Uranus and Neptune have changed places. You can see that now the solar system has the right structure. And that's part of the reason why we think that this is a genuine scenario for the solar system. This is a very common process, we think, for solar systems in creation, because they all have these kind of planetesimals that get scattered, and then you get scattered until you get planets into resonance, and at that point everything creates havoc. You get chaos. And you can have these impacts. You can transport cometesimals, cloud material from the outside towards the inner planets. And so this is then sort of the summary of this. We have things happening in the interstellar medium. You have the stars and planet formation, and then you can deliver material to an early Earth, either through asteroids and cometary particles coming in, or to interplanetary dust particles or meteorites. And then once you're on the Earth, you can, of course, have further chemistry taking place. Now, I made this point that you get things delivered from different places in the solar system, and that will determine what the composition of your planet is. And that's an important point that I want to make, is that that determines what the atmosphere of your planet will be. These are 2 calculations, one for an H chondrite, one for a CI chondrite. These are 2 types of meteorites. These are your typical stony meteorites. These are the carbonaceous meteorites. And they have a slightly different composition. If your planet is made up of these H chondrite kind of composition, then what you have is mainly a methane, water, and ammonia material. And that means it's very reduced. That means that you can have a Urey-Miller kind of chemistry taking place. That means that if you create some energy through lightning or some other way, that you can transform some of the methane into formaldehyde. Formaldehyde in the presence of ammonia in a watery environment will have a Strecker reaction, will start to make amino acids. That's how you can make the building blocks of life on this kind of a planet. On this kind of a planet, it's actually very different. Because on this kind of a planet, you have water, you have CO2, it's a very oxidized environment. Here, Yuri Miller will not help you. If you have a planet that consists of this, if the Earth started this way, then it means that the building blocks of life would have to be brought in from outside. And they could have been brought in by, say, the meteorites or the comets. And if that's the case, then life would have started very differently. So that's where astrochemistry comes into astrobiology. It's setting the stage of what is the composition of the atmosphere, of what is the composition of the materials that you have available to start building life in this environment. And so the molecular history of life really starts in the interstellar medium. And molecular clouds in the interstellar medium are the birth sites of stars, and there's a lot of interesting chemistry that takes place in those environments. Now, when I started in this field 40 years ago, interstellar chemistry was understood. It was really very simple. It was ion-molecule reactions. You had cosmic rays which ionized the gas, a little bit of ionization that drove the chemistry, and you made some interesting molecules. And it looked like this jigsaw puzzle. We sort of knew many of the pathways. Some parts were missing or not fully understood, but it was just a matter of a few years, and we would have this all sorted out. And that has sort of changed. There are some successes for this ion molecule chemistry, but I think the main point to take away is that what ion molecule chemistry does is lock all the carbon up in CO. And CO is not very reactive. If CO is your main carbon reservoir, it's very difficult to get it to do organic chemistry. And it's very difficult to get it to a terrestrial planet. And so that has changed over the last 20 years or so. And we still think that you can start with atoms and build them up one atom at a time into larger molecules. CO or methanol and even larger molecules. You lock those up in comets and asteroids and then deliver them to the Earth. But there is also a second way on how you can form molecules and can build the organic inventory of space. And that's when you start with stars. Stars in the last stages of the revolution, they eject most of the material back into the interstellar medium. And the material is enriched in their nucleosynthetic products, but mainly the main point is that it is fairly warm, it's fairly dense, and when it flows away from the star, it will cool down, and the chemistry that takes place is the same chemistry that you used to drive up to hear this talk. You know, it's the same chemistry that plays a role in sooting candles or in car engines. It's soot chemistry. Once you have those molecules in the interstellar medium, because you're ejecting them from these stars, then you can drive a very interesting chemistry through the energetic particles or photons that are available. They can break those molecules down to smaller molecules, which then get locked up in the asteroids, comets, and delivered to the Earth. There are many different species present, processes that play a role in this. I'll highlight a few of them. But I think I should start first by showing you this slide. This is what the ion molecule chemistry was that we were talking about. It looks very complex, but basically takes carbon and it locks it up in CO. All the arrows go to CO, and that's just kinetics under the conditions of the interstellar medium. That's the pathways that are accessible to you. And CO is a very sturdy molecule. It's very difficult to break out. And so all the carbon is locked up in CO. And that's just gas phase chemistry. We have learned that there's also a lot of chemistry taking place on small dust grains. Dust grains are sort of the meeting place where species come to mate and drive interesting chemistry. And basically, because you're on the surface, you have a lot of time to collide. And if you have a lot of time to collide, you can form interesting species. And this is just to show there's a spectrum from about 2 to 25 micron of a star embedded in one of those molecular clouds. And you see broad absorption features due to simple ices, like water, ammonia, CO2, and methanol. And so there's a lot of interesting chemistry that takes place on these grain surfaces, and that can drive your chemistry away from the CO. And this slide sort of summarizes how that happens. Here is CO, and it's very unreactive in the gas phase, but on a grain surface, it can react with atomic hydrogen. There's a large barrier, but because you're on the surface, your hydrogen can actually tunnel through those barriers because there's so much time. It can sort of react with these COs for the time that it resides on the grain surface, which may be a day. And so because you have a day at a time, the reaction can occur. And because the reaction can occur, you can hydrogenate CO, you can hydrogenate all the way to methanol. And at the same time, you'll hydrogenate your oxygen and form water. You form a mixture of methanol and water with some CO2, where you mix the two chemistry because you have the OH reacting with the CO. And so you get a very different mixture than what you would get when you look at gas phase chemistry, because you can activate the carbon that's in the form of CO and turn it into methanol. And we've learned that this chemistry can drive an interesting chemistry in the gas phase afterwards, because when those ice particles get close to a newly formed star, they will evaporate, they will release their gases into the gas, and in the gas, all of a sudden you don't have CO, but you have methanol. And methanol likes to transfer the metal group. And when it transfers the metal group, you can make other species like dimethyl ether and more complex molecules. They're all still fairly simple organic molecules consisting of a few carbon atoms with oxygen and some hydrogen. But it is much more complex than the CO that we started with, and it's much more interesting when you start to talk about the origin of life. And there are some different models that have been proposed for their formation. I want to highlight one here. That's this one. This is time, this is the composition. And it starts by a star evaporating the ices. So you start off with a lot of methanol in the gas phase, some formaldehyde. They start to react with each other through ion molecule reactions, and you form with a dimethyl ether metal formate. And it takes about 10 to the 4 years. And we see these kind of molecules. We see these kind of molecules around these kind of stars. And all of a sudden, when we tell this story to astronomers, all of a sudden we are their friends. Because all of a sudden they realize, oh, look, you have a time scale here. So we can time the process that's taking place, the astronomical process of the formation of these objects. You can time it of the order of 10 to the 4 years. And that's a very interesting time scale when you start to talk about the evolution of stars in the early phases of their formation. And there are some issues with this, so this may be another way of forming complex molecules. This was a experiment that was done in a droplet. So there is a charge, a sodium atom, surrounded by methanol molecules. And those methanol molecules can react with each other and form a dimethyl ether by forming water. And it's the same kind of chemistry. It has some advantages to do it this way. And this may be a process this is in droplets, but may also take place just before the evaporation of these ices in the ice phase. So that's a different way you might do a similar kind of chemistry. It's again ion molecule chemistry, but now in the ices. There are other processes that people have talked about that have to do with the photolysis of these ices, in which you can knock off hydrogen atoms or OH radicals from the molecules that you have formed by the grain surface chemistry, by UV photons, and then you can have those fragments react with each other and make complex species. So there's a rich chemistry. Once you have broken the carbon out of CO by making it into methanol, once you have done that, you can drive a rich chemistry. That's, I think, the bottom line. And that may have some bearing on the formation of the chemistry that took place in the formation of the solar system. What is shown here is the abundances of certain molecules in protostellar environments, so the ones that we observe in space, and it's plotted here against the abundance of those same species in comets. And you can see that there is some sort of trend. I've labeled them differently, but there is some sort of trend that indicates, well, maybe the kind of processes that play a role are the same kind of processes that play a role in the formation of comets. So I've talked about one branch of chemistry here. I've focused on this branch, where you go from small to big. Let me now look at the other branch, from big to small, where you start off with large molecules, and we're going to break them down. But let me first start off by showing you some indication of why we think these molecules are very abundant. And it's basically these kind of spectra. These are spectra from 3 to about 20 microns, and you see these broad emission features present. And these are very characteristic for polycyclic aromatic hydrocarbon species, PAHs. And they are very abundant. About 5% of the carbon in the universe is locked up in these kind of species. These are very relatively complex species. We're talking about 50 carbon atoms, and they're ubiquitous. They're everywhere. And let me show you an example of that. This is the Orion region. You may have seen it. This is here are some young stars. They are very hot. They ionize their environment. This is plasma. The plasma is recombining, and so in your optical eyes, you see the red glow from this recombining plasma. Now, this is what you would see if you optical. This is what Huygens saw in 1650 or so, and this is what you would see if we had molecular eyes that were sensitive to the light that emits by molecules. Same region. Here are those bright stars. They are illuminating their environment, and as they are illuminating their environment, there are these large polycyclic aromatic hydrocarbon molecules. They absorb these UV photons, they get highly excited, and they relax with the emission of infrared photons. And it's these infrared photons that you saw in that spectrum, these infrared photons that we collect here and give this red color, this false color image, of course. They give this red color so to show you how far these stars interact with their environment. This is a scale of a few light years in this region of massive star formation. Here we're looking at a whole galaxy, M51, the Whirlpool galaxy. A nice nucleus surrounded by these beautiful spiral arms. You see all these blue dots here are the kind of regions like Orion, like I just showed you. They're all massive stars that are interacting with their environment. And this is, again, optical eyes. Here is what you would see if you had molecular eyes. And you can see that the whole galaxy is now glowing in the light of these molecules. This is on the scale size of 50 kiloparsecs. This is the whole galaxy is a glow. You can see if you look at these kind of wavelengths, the only thing you would see is really these kind of molecules. It's clear from looking at these pictures. It's clear that these molecules must be very important. They are everywhere. They are transferring UV light into infrared light. They are ubiquitous. And so much effort has been going over the last 10, 20 years in trying to understand these molecules, trying to understand what their role is in the chemistry. And these are the kind of molecules that we'll talk about, the chicken wire molecules, benzene rings fused together into flat species and decorated with hydrogen atoms at the edges. And then they are a little bit larger than what is shown here. The typical one contains of the order of 50 carbon atoms. So they're relatively large molecules, certainly when we talk about molecules in space. And we have the same problem. We have the same problem that we had for CO. How do we get the carbon out of the CO and activate it? Now we have the problem, how do we get the carbon out of these PAHs, these large molecules, and how can we activate it and drive some interesting chemistry? And just to show you that there's a relevance for the reason that we're talking about, this is an image of a protoplanetary disk around a star. Here's the star. This scale size here now is the scale size of our solar system, a few hundred AUs. And the green color here is the light of the fluorescence from these molecules. So the whole surface of this cloud, of this disk, is set aglow by these species. And you know, it's a little bit foreshortened here because you're looking into a ball and you're looking in it under an angle. Yeah, but it's the whole surface of that ball that's being illuminated. And when we look at the characteristics, we have to use infrared spectroscopy to study the composition of these species in these environments. And these are 3 of these kind of environments and 3 spectra. They come from similar kind of stars, so they see the same kind of shining light, so the excitation is very similar, but they have very different spectra, and the difference in the spectra must mean that there is a difference in their chemistry. This is the kind of a fairly large distance in the surrounding cloud. This one is from material that's right in the disk. So between the cloud phase and the formation of the disk, some chemistry has taken place and has changed the composition of what you started with in a different composition. It's that kind of chemistry that we like to understand. And that kind of chemistry is difficult to study in this environment because we don't have enough spatial resolution to really study it in detail. But fortunately, nature is helping us here because we can look at the different regions where we understand the conditions better and where we can then study the process that play a role. And this is one of those regions. This is a bright star, HD 200775, and it's illuminating a molecular cloud that you can see here, and this is the boundary of that cloud. And we can take spectra. We have taken spectra of this region here, and they're sort of summarized here. And here are 2 of those spectra, number 2 and number 1. And if you look at number 1, you see only these PAHs. You see the signature of these PAHs, so that's far from the star. You see only these PAHs. But when you get close to the star, you actually see the signature of C60. C60 is a soccer ball, a molecule in the form of a soccer ball. And you see that only peeking up when you get close to the star. And we can analyze this data, and this shows the results. This is the abundance of the PAHs as a function of distance to the star. And far from the star, about 10–15% of the carbon is in the form of these large molecules. But when you get closer, they get destroyed. And close to the star, you only have 1% of the carbon left. Yeah, on this side, you see in this panel, you see the C60, and the C60 does just the opposite. It starts with a low abundance, about 10 to the minus 5 of the carbon, but when you get closer, it's about 10 to the minus 4. And this is curious because it's very tenuous there, and it's very difficult to make a molecule as large as C60. And so what we think is happening here is that you destroy the PAHs, and while you're destroying it, some of it gets transformed into C60. And that the schematically shown, you start off with your PAHs here. And the first thing that will go is, of course, the weakest link. The weakest link is always the one that goes first. And the weakest links are the hydrogen atoms. So you strip off the hydrogen atoms and you make graphene sheets. And then once you have made graphene sheets, you can knock off the carbon atoms. Once you knock off the carbon atoms, you can make flats, rings, chains, and eventually atoms. Yeah, but while you're doing that, you may also be able to transform some of the species, some of the graphene sheets, you might isomerize them into cages and in fullerenes. And so we have been studying this in the lab. This is our experiment. It's an ion trap where we ionize our PAHs, we put them in a ion trap, we shine with a laser on them, and we start to strip off the hydrogens. That's what you see here. And it's easier to strip off the odd ones than the even ones. But eventually you wind up with the pure carbon sheet. Yeah, and if you then increase the laser power, you can start to see that you start to lose C2 units as well. And you start to break down C2 units until you get to C32, and then you jump over to the chains on this end. And this is very similar to the kind of chemistry that has been studied for fullerenes. And this is an example here. You have C60. You start with C60. You knock off 2 carbons at a time. And as you do that, the cage will slowly shrink until you reach somewhere C32. Here, C70 goes the same way. You break it down. When you reach C60, it's, of course, a little bit more stable than its neighbors. It's a very stable molecule, and so its abundance is fairly high, but eventually it gets destroyed as well. Here are your PAHs, C60. You break off the hydrogens. You have your carbon skeleton, and you break them down 2 and 2. And you can see that you see similar kind of magic numbers appear where abundances of certain species are more favorable than others because of their stability. Here's C66, and you do the same thing. You break off all the hydrogens, then you start to break off the carbons. You also make a little bit excess of C60, and then you break it further down. Now, this is at a slightly different wavelength, and at this wavelength, C60 doesn't absorb. So even at 120 millijoule, C60 just stays C60 because it doesn't absorb photons. If you take C70, it does absorb. You break it down until you reach C60, and at C60 you stop because that's a stable molecule that doesn't absorb. So that's where you stop. Here's the C60 H22. You start to break it down, and it just happily breaks down, and you don't see much evidence for the formation of C60. But if you start with something bigger, here's C66 H26, break down the hydrogens, then you break it down, and at C60 it actually stops. There is some going down, but there is a large fraction which stays here and which is stable. And so we think that what's happening here is that you are actually summarizing some of those PAHs, some of those graphene sheets, and you produce these species, these fullerenes. Yeah, and so this is, we think, one of the key chemistries that takes place in breaking down the PAHs and making that carbon available for further chemistry in an environment and into molecules that are of much more interest if you want to build life. So these were the key questions that I started off with. I focused on the second one, and what we have found is that really the organic reservoir of the habitable zone depends on how you get the carbon out of CO and out of PAHs. For CO, it's grain surface chemistry, where you activate the CO, you form it into methanol, and the methanol can be driving an interesting chemistry. For PAHs, it's photolysis, which leads to fullerenes and hydrocarbon radicals. And then the pH can also be broken down by warm chemistry in the inner solar system. So these are the new paradigms. I really want to stress that these are paradigms. This is what we think the chemistry is taking place. They are very precise descriptions of the chemistry that we think is important and for the formation of the organic inventory for terrestrial-like planets. And the goal for our future is, of course, to determine whether these paradigms have anything to do with reality. They are very precise, but are they accurate? And we want to be able to predict what the composition is of terrestrial exoplanets, exomoons. We want to link that to the processes that take place in their protoplanetary environments. And we want to predict what the biosignatures are for these exoplanets. And then I started off by saying that we live in a very fortunate time, and it is amazing, because we have all these missions going on, trying to tell us all these, study all these processes in the thing. This is, of course, Kepler, where you're measuring the transits around stars, and as the planet moves in front of the star, you can see this little dip in the light curve, which tells you what the planet is and where it is. And what it is doing. This is ALMA. This is a radio telescope working at sub-millimeter microwave frequencies, built on the plateau, the Atacama Desert in Chile. It's about 60 dishes that are working together to mimic a big telescope, and is going to revolutionize our understanding of the gas phase composition of these molecular clouds. This is Sophia. Sophia is a Boeing 747, which has been transformed. There is a cavity in the back with a large telescope, a 2.5-meter telescope. You fly above the tropopause, so you fly above most of the water in the atmosphere, and you can observe many of the molecules in space. And so this is a great observatory to study the composition of molecules in the infrared. This is James Webb. James Webb is a 6.5-meter telescope 6.5 meters. That's enormous. It's the Hubble, for comparison, is 2.5 meters, so it's a much bigger telescope. It's going to be launched in 2018. It has a lifetime, expected lifetime of about 5 years, and we're going to use to study the kind of molecules like PAHs in the interstellar medium and in everywhere in the universe. So this is on the astronomical side, where we're studying the composition of the molecular universe. Similar things are happening on the planetary sciences side. This is the Cassini mission, where the Huygens probe was dropped into the Titan atmosphere. And Titan is an atmosphere. It's much colder, of course. It's much further out in the solar system. It's much colder, and the Titan atmosphere consists mainly of methane. And so you see these structures here which resemble stream beds, but it's not water that's flowing here. What is flowing here is methane, and there are methane lakes. And there's a very interesting chemistry. If our early Earth had a methane-rich atmosphere to start with, then this is maybe a very interesting analog to see what the kind of chemistry is that's taking place in these environments. Here's Rosetta. Rosetta is a mission by ESA that sent a lander to the surface of a comet. Here you can see it, studying the composition of that comet and the structure of this comet. And we get our first results, and they look very interesting on that. This is the Stardust mission. The Stardust mission was a mission that was sent out to a comet. It had a little styrofoam shield that it folded out and that collected some of the material that came from that comet and collected that in that styrofoam in a fairly gentle way. It folded it then back in and then transported it back to the Earth. And this is the first extraterrestrial material that we have gotten since Apollo. You know, it's amazing. Of course, Apollo brought back a few kilograms, or tens of kilograms, I think, to the Earth, which have been studied for ages by our cosmochemistry friends. This brought back, I think, a microgram. But it's, our techniques have become much more refined, and so we can analyze a microgram. And we can find very interesting species, including we have found amino acids coming in this material from these comets. So the amino acids can be formed under cold environments, in a cometary environment in this thing. This, of course, the rovers on Mars, and this Curiosity. And the nice thing about Curiosity is that it has a little spoon. Huh? It can dig into the ground and pour it into a cup and then analyze the composition. And so that's one of the key things, of course, that these rovers can do. They can study the composition of Mars and look for signatures of life. They have not found life yet, but they have found various signs of water, and that's very exciting as well. This is then the last one that doesn't have a video yet. That's JUICE. That's a new mission from ESA. That's a mission that's going to go to the icy satellites of Jupiter. The icy satellites have a thick crust of ice, but underneath that ice is an ocean. And that ocean is being kept there because of the tidal interaction with Jupiter. And if there is organic material in that ocean, then well, maybe life could have started there as well. And so this mission is designed to sort of study these environments and see whether the organic material could be transported from the surfaces through the ice, through cracks or whatever, to these oceans, and whether you could have some interesting life to take place there. And so I've taken you through a tour of the molecular universe, taken you through a tour of all the things that I have worked over the last 20 years or so. But I want to end with a little note for basically for the students, the grad students and young postdocs. You know, we sent up these missions. They cost $1 billion or more. You know, and maybe in Microsoft that is not that much, but I think you could buy a few bankers for that amount. Yeah, and Yeah, we get a lot of data home. And our engineers are happy because we get data home, we can store it, and it looks great. But the science that we get out of that data, the science that we get out, in the end, depends on those lone graduate students working in the labs, trying to find out what the ways are, how you can relate the images or the spectra that we see into actual facts. And so that's something that we will have to keep doing for the next 20 years. But you can see from the missions that I just indicated here that the future is very bright. Thank you.
So I'm just going to ask the first question, and then I'm going to come around and so stick up your hand if you have a question. Thanks, Cliff. So Xander, if I could start with a more speculative question. So knowing what you have acquired over your time in your career, what's your feeling on the evolution of life, or sorry, the origin of life? Could it have happened out there and then be transported in with the material? Or, you know, I invite you to speculate.
You mean could we have panspermia?
Right.
Undoubtedly, it has happened. You know, undoubtedly, things can be transported over a solar system scale size. Whether you can do it over a planetary stellar scale size, yeah, likely. Because life is very tenacious. Life can survive once you have formed it. It can be transported up and be. But that's the way you would do it? No, I would not, because it's so easy to make complex species. You know, if you want to make life, you don't need to find a way of spreading it from one particular source. It's really very easy. That's what I take away from this kind of chemistry that we're studying. That's what I take away from all the studies that we have done over the last so many years.
So going back to your various graphs about solar system formations, with like the little bouncing planets and things like that, I like that one. I'm wondering if any of the work you're doing on the chemical interactions, the modeling part, would shed some light onto just what exactly super-Earths are in other solar systems, since we don't have an analog in this solar system.
Well, in the end, of course, what we want to do is study the composition of these atmospheres. We're not really yet there, but James Webb may well do that. And then we can determine what the atmosphere consists of. And that will tell us perhaps where it came from. Even a simple question like, does it have CI kind of composition, or is it ordinary chondrite? That may be telling us a lot. Or maybe it came from comets. That will be a very different composition as well. We haven't really played this to the extent that you want us to do, that we want to you take these scenarios and see what the composition is of your planets, and then predict what the composition is of the atmosphere. But that clearly is the next step to do.
Other questions?
I take it when you said it was very easy, you're talking about it's easy to make the molecules of life.
Yeah.
But who has taken non-living molecules and mixed them together and come up with something crawling?
Nature has done it.
No, but do we have any examples besides Earth? I mean, can we do it ourselves in the lab?
No,
I
know. I mean, we have not been able to do that, but that may be because we are not as clever as nature. I think the message that I took away from that timeline is that apparently it is very easy. 200 million years after you could start to form life, we had life, we had fossils. You know, so it must be very simple.
We don't know where they came from, though. They might have come in.
That's granted. That's true.
Still a big mystery.
Yeah, but that would have been at a late. Yeah, but then you're just playing chicken and egg, huh?
I'm worried about the canning industry.
Yeah.
We produce billions of cans,
Yeah.
and we take life and we cook it to where it's no longer living, and then it sits in the can, and none of those billions of cans ever spontaneously generate life. And they've got all the organic molecules, you know, in there necessary for life,
Yeah, I mean,
but they don't.
you have to add energy. Once you start to add energy, or you start to drive some interesting chemistry, you open up the can. You know, and you let it stand there, it will spoil.
Yeah. Well, yeah, it does. But I mean, you have cosmic rays and so on going through the cans.
Have you kept the can unattended for 100 million years? When you do that, then you.
No, these are very interesting questions. I don't want to knock these questions. These are very interesting questions, and it would be fun to be able to answer them. And once I have a graduate student for 100 million years, I'll have the answer for you. Hans.
Well, thank you, Xander, for a very exciting talk. I do have a challenge for you.
Yeah?
And that is, I mean, you picked the timeline and you said, well, okay, looking at that timeline, it's probably easy to form life after the late heavy bombardment. But is that really logically stringent? You know, it could still be the exception, because many circumstances could have conspired in the case of the Earth that this happened. And in other cases, it was not so easy. So how would you respond to that challenge?
It's possible that many other factors play a role, and we haven't deciphered those yet. I think the next step for us to do is to go and characterize the atmospheres of these exoplanets, see what the composition is of their atmospheres, and then build on that, start to think of what are the biosignatures that we would accept or life has evolved there. It's a stepwise process that we have to go through. We have made the first few steps, and you know, by golly, I didn't think 30 years ago that we would be where we are today. Yeah?
All right, Xander, we have a special SETI Talks bug there. There's actually a couple of robots from the future. I'm sure they're still discussing the question of the origins of the life that led to them and so on. So, you know, if you put your ear up to there later at night, you might actually hear some of the answers come through. Not guaranteeing anything, but please join me in thanking Xander for his fascinating talk. And if you have any questions that you didn't want on the record, then please come